Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Intel. We have James Reinders. He's the director and the chief evangelist for Intel's tools. So, James, welcome to the show today.
My pleasure to be here, Rich.
Hey, it's nice to talk to you once again. And it's about that time of year where Intel does a refresh of their compiler and tools for parallel programming, and I thought we could catch up, and I brought your slide deck up here. Why don't we start with that?
Well, excellent. Yeah, it'd be my pleasure to talk about what we're doing. As you said, each year we generally get a new version of our tools out, and this year is no exception. So I'm happy to be introducing Intel's Parallel Studio XE 2013 and a superset of that called Intel Cluster Studio XE 2013. And Parallel Studio is available immediately, and Cluster Studio, which includes support for our MPI analysis and library, will be available in a couple of months as a follow-on to this. But I'll be very excited to talk about the features of both of them with you.
Well, terrific. Well, why don't we save Q&A towards the end, and we'll go from there.
A lot of things are changing in the environment that motivate us in our tools. Bottom line for us is helping developers get top performance out of the hardware. Whether you just want to do that with using recompiles and linking with different libraries, or whether you want to dive down with an analysis tool and take a look at TLB misses and detailed activity in your program, we support that full range. And we're really looking at an environment where multi-core and many-core are realities today, where vectors are getting wider, where there's a lot of different things going on in the hardware that give us opportunity or work to do to take advantage of that in a performance-oriented way. And that's really what our collection of tools is all about, is helping software developers gain the insights and have the tools necessary to do their jobs. I've got a list here of the top features, and I think some of these are things you would expect from Intel every year, and some of these are interesting new functionality that's been inspired by our customers, and we're pleased to be able to offer that complement the general push for performance for the latest processors. So, of course, for processors themselves, we've got tuned support now for Ivy Bridge microarchitecture. We've had support for this microarchitecture in the past release, but we've had a year more of experience on it, and that allows us to do tuning based on customer feedback. We also have support across the board in our tools for Haswell's microarchitecture. Of course, this is in advance of the introduction of any products using that microarchitecture, but the fact that we have it there allows our users to get their software ready as well for Haswell microarchitecture-based products. And we have our full support for Intel Xeon Phi coprocessors. So this is, of course, the first product that will use the many integrated core architecture, commonly referred to as MIC. This is a coprocessor that will have more than 50 cores in it, and excels at extending Xeon's product line into highly parallel applications. So all the tools people are familiar with, the Intel compiler, C, C++, Fortran, vTune, our libraries like MKL, all of them include support for these microarchitectures and the Xeon Phi coprocessor. So you don't need to learn new tools. We just keep updating them for the latest offerings. And of course, we invest in standards, which I have off to the right, expanded C++, 11, and Fortran 2008. I don't think anyone has these whole standards implemented yet, but we're working at being a leader among those to keep adding the functionality, and we're quite far along in both of them, and MPI 2.2. But if we take a look at some of the exciting features, that our customers have helped inspire, we have customers that have different needs. One of the areas has been programs that include Java code, and we have an exciting capability to do a very low overhead Java profiling. This allows us to do statistical sampling, which gives a very predictable overhead, very low, but still extend our analysis capabilities into sections of code that may be running Java code. We also have the ability to pay attention to sleep states and show them in a time graph. And I think those are both very exciting new capabilities for analysis that shows you what's really going on the machine, which ultimately lets you tune it for correctness and performance. Now, as far as reliability goes, we've got a really nice new capability called Pointer Checker. We have a capability to monitor the growth of Heap allocations, and we have some capabilities with the hooking into the Berkeley Labs checkpointing system to improve fault tolerance with the use of MPI. And then probably the most commented on new feature that we have is this conditional numeric reproducibility, or the ability to ask the math libraries in OpenMP and TBB to take floating point operations and make the results of them predictable from run to run, to eliminate the round off errors that lead to FP operations not being associative, make them predictable, the order they'll be done in, so that you get the same results run to run, subject to a few conditions, like running on the same size machine each time. So that's kind of a high-level overview of all of these, and I've got some slides I can go through fairly quickly and sort of point to a little bit more detail on each of these, and hopefully get our listeners excited about the capabilities that these tool suites bring to bear, so that they can get their work done.
Sounds good.
I've got some benchmarks here. I'm showing spec int, spec FP, both of them the base numbers, and polyhedron, both on Windows and Linux, and comparing them to some of the common offerings out there, if you will. I think the leaders in the field at offering products that people use. So, obviously Microsoft Visual Studio and their C++ compiler is widely used on Windows, and we have a substantial performance advantage in our ability to deliver performance to the end user's application. And the same thing's true on Linux. With the GNU compiler, we're able to offer performance advantage on these benchmarks, and I think that's widely applicable. We work very hard at giving a good performance experience for people that use our tools. And then the polyhedron benchmarks, a pretty consistent leader in those benchmarks, other than Intel, is ABSoft, and even over ABSoft we can offer a substantial performance advantage based on our measurements on polyhedron benchmarks, which are widely used by Fortran developers. This also extends to our libraries. I've got a chart that shows MKL benchmarked against a very popular open source package that does similar math libraries, in this case LAPACK. And we're very proud of our optimizations that get good performance. And one of the characteristics of our libraries is we work very hard to make them less sensitive to various block sizes, the size of the problem. Quite often people look for a sweet point when they benchmark a sweet spot in their performance and by sizing it correctly. And we've worked very hard to make it so that our library is less sensitive to variations in problem size, and I think that shows pretty well on this graph. It applies to our Intel Integrated Performance Primitives, or IPP library, as well. We, on this particular graph, lower is better on this graph, opposite of the graph for MKL, and we're able to take great advantage of AVX, for instance, and push down the time to execute based on that. get really great numbers, and you're able to build a single binary that runs on machines with and without AVX and will automatically take advantage of AVX for you. I've got a graph that kind of reiterates the fact that, all of our tools are working hard to support the latest hardware so that developers that are working to take advantage of this hardware or to release their software supporting it have the tools they need, whether it be tuned Ivy Bridge microarchitecture or it be being ready for products based on the Haswell microarchitecture, or of course the Intel Xeon Phi coprocessors. Across the board, we've got support in our compilers, our libraries, our parallelism libraries, our analysis tools, and our debugging tools to be ready to support this and help get the developer able to get optimal performance. Now, VTune, on a slide I have here, I have a dozen new analysis features for VTune, and I can talk about a few of those. I'm excited about all of these. They're very innovative things. What really excites me, of course, all the time about VTune Amplifier is its ability to show me what's going on the machine, because I can't really lift the top off my computer and see what's going on in it very well. VTune shows me what's going on, and anytime it surprises me, that's really gold. It tells me the program isn't operating the way I was hoping it would, and that usually gives me what I need to figure it out. So I mentioned before, low overhead Java profiling, definitely a great thing to be able to associate with Java, and we're able to support multiple Java JVMs running on the same machine, which has turned out to be common these days. And so previously we had had some support some time ago, but we'd only hooked to one JVM. And so this is pretty exciting to have new and better capabilities here. For power analysis, we have the ability to show time graphs and show what sleep states the processor is in. And for a lot of developers that are sensitive to trying to keep the power usage down, either in a handheld or an embedded situation, or also potentially in some data center applications, wanting to make sure that when you think your program is acquiesced, when you think it's not supposed to be consuming power, that that's really happening. Surprises in this area can cost you a lot in terms of either battery or expense at running a data center. Now, the pointer checker capability is a novel new thing we added to our compiler, where the compiler will look at every pointer that's used, and it actually extends what's in a pointer. A pointer is not just a single pointer, but it'll be a pointer along with a upper and lower bound. And so, for instance, if you do something simple like malloc some memory, the compiler assumes that the pointer that gets that malloc value in it should only point to memory that was malloc. It shouldn't point outside of that range, or if it points to an array or a structure. And then what it does is it adds checks at all the usage points to see if that pointer is still within those bounds. This has just been tremendous. Users are very excited during the beta that they ran this on their code, and it would create a breakpoint in the debugger and tell them, hey, something's wrong here. This pointer is not pointing to a place that should be legal. And they'd look at it and go, oh my gosh, how'd that happen? And you'd be able to find it and debug it. Really a neat new capability. Now this is generally just useful for every program, but I think in this day and age of writing parallel programs, anything you can do to get rid of any bug in your program is helpful, because when you get doing parallel programming, you want to get rid of all the easy sequential bugs that you can, or if your parallelism is causing you to do pointer corruption, it's useful to have a tool that'll help you debug that. And along those lines also, we have a new heap growth capability. Pretty simple idea. Instead of just looking for normal memory leaks, which is when you have memory allocated that you never deallocate, but you quit paying attention to, you quit having a pointer to, there's also this other type of bug where for some reason part of your program is accumulating memory. It may technically still have a pointer to it, but it never plans to use it, and your program gets larger and larger. And I think all of us have had applications that have bugs in it like this. They're usually someone else's application, but an application that you run for a while, and if you exit the program and start the program again, it'll run faster because it's been accumulating memory it shouldn't have been holding on to. So we have a tool capability to help you find that. And that's a pretty good rundown. I've got, there's other great features. One that will be along with the Cluster Studio XE is using the Berkeley Labs checkpoint restart facility with our MPI library is very exciting. And I definitely should talk, just make another plug for the numeric reproducibility that I have a little bit more detail on. But our math kernel library, OpenMP, and threading building blocks all support some new features to allow you to specify that you want the order of computations and the order of parallel reduces to be consistent run to run or processor to processor. And that gives you a reproducibility capability that can be really useful in validation or acceptance test and the likes to help you have confidence in your program, or maybe to debug other aspects of it, knowing that every run should produce the same answer. I think that's a pretty good rundown of the features we have. And slide 19 has a little bit more information about pricing and availability. Parallel Studio XE is available immediately, and Cluster Studio XE will be here soon with its extended capabilities for MPI.
Well, terrific. Well, thanks for that, James. A couple questions here. Let's start with the most recent thing first. The conditional capability that lets you get the same answers with is that due to floating point roundups and things like that you want to execute in the same order to get the same answers every time?
Yeah, absolutely. It's completely because floating point operations have round off. So the order that you do the math in can produce slightly different answers, even though you've technically done the same math. Changing the order, and that commonly happens in parallel applications where you might do something like a reduce operation, where you divide up the problem across lots of cores, and then you add the sums together that each core came up with, and the order that you do them in matters a great deal for the exact answer you get. Not necessarily whether it's right or not, but whether it's exactly the same answer.
Sure. And then, with your hardware support, earlier on you talked about supporting the Xeon Phi, which Intel announced the brand earlier this summer, but the hardware is expected later this year. James, why is it important to have the software and the tools out before the hardware?
Well, we always work to have our tools ready because there are other companies that'll be looking to have their software available when the products launch. So if we just showed up with the Intel tools at the same time as the hardware, obviously it'd be difficult for other people to have their software ready. So we make ours available in advance, and that gives added opportunity for other software companies to have their products ready at the time that we introduce our silicon products.
Terrific. Well, kind of a wrap up here, James, as we look out here, you have the Intel Cluster Studio. Is that a new family of products for you guys, or is that just a continuation?
Well, it's a continuation, but it's been growing, and it's gotten different names over time. So I think the first time we used the Cluster Studio name was a couple of years ago, and the Cluster Studio XE name I think we first used a year ago. But the tools in it are been around for a long time. They're very proven. A little bit of extra marketing names around it to give it a clean name and a single package that includes all the different tools a software developer would use to get the best performance. That's what's in Cluster Studio XE.
Well, terrific. Well, James Reinders, I want to thank you once again for coming on the show today.
It's been my pleasure, Rich.
You bet. We'll talk to you soon. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.